factor, but what we really need to understand is that the current gain is the ratio between the collector current and base current. So beta, or H of FE, somebody put that, but that's just the same thing, right? So H of FE, or beta, which the book calls it, is IC divided by IB. And of course, which is the biggest current in the transistor? Yeah, so IE is equal to IB plus IC, and then we can just arrange this formula. So IC would be equal to IE minus IB, and then IB would be equal to IE minus IC, if we rearrange that one formula. So the biggest current obviously is the emitter, because the emitter handles both IC and IB. So that's why the emitter current is the greatest. Now, for calculations, we're going to assume that IE and IC are equal to each other, but that's not exactly true. It's just that IE is approximately equal to IC, right? They're really, really close. But for calculations, we know we have all these tolerances and everything that for calculations, there's so little difference between IE and IC. We know that we can use IE. If we know IE, we can use it for IC. If we know IC, we can use it for IE for calculations, right? You understand? Because all our calculations are approximations anyway. The problem we have is that our math is exact, right? You understand? But our components are not, right? So there's very seldom that you'll ever calculate where you'll come up with exactly what you measure, unless you measure all your components. So back in DC, what did you do? You measured all your resistors, right? So you didn't, when you did your math, you didn't do the color-coded value, you did the measured value. So that means your calculations and your calculations and your answers were the same. They should have been really, really close. But now we're not going to do that, right? Because we know that we have all these tolerances. So the problem we have with beta is that it's all over the place. So for the 2N3904, which is 2N, basically 2N means it's got two junctions, right? 3904, and then these are numbers assigned by JEDEC, the Joint Electronic Device Engineering Council, as these things are registered. So that's about the only way they sign the numbers. And so the 2N3904 is a JEDEC registered transistor, which means basically anybody can make one as long as it meets the specifications that they say. It has a beta anywhere between 30 and 300. So what am I going to use? Huh? Well, then that means I'm going to expect to gain. I'm going to expect that would be like me expecting a pay of 300, and my boss says, "Well, I'm going to pay you between $30 and $300." You think that your employer is going to pay you $300? No way. They probably want to pay you 30, right? You understand? But it's going to be somewhere between that. Now, the problem we have with beta is that it varies with temperature. So that means even if I've got a beta, if I don't do anything to take care of this and figure out what I can do to change that, then the temperature varies with beta. So what I did is I came up with a circuit that I've got wired up here so we can look at this. And it's a real basic circuit. We've already seen the circuit a couple times. It's a dual voltage bias circuit. And we'll see how my calculate. So typically for the 3904, typically we can use a beta of around 100 just to start off with. And beta has no units, right? You understand, because it's a multiplier or divider. So over here, I got a 5 volt supply. So let me say that I'm going to show you the actual circuit. So I started off with a 10K pot. And what do we do with the potentiometer? Yeah, we can vary a voltage, right? So this is 10K. And then I came over here and I had a resistor that I wanted to figure out what I wanted to use. And then I came over here and I know I'm going to get a lot of gain. So over here I used a 1K resistor. And over here, this is plus 5 volts. And then over here, I'm going to use plus 12 volts. So we call this guy VCC. Why do we call that VCC? So when we duplicate letters, that means it's a power supply. And it's what lead the power supply is predominantly connected to. So what's it connected to? Okay, it's actually, okay. So this is a NPN, right? So this is actually, and this is the one that's not the common. So this is VCC. What would be this guy? B what? BBB, right? And we don't have, technically, we don't have a VEE because it's connected. It's the common for the circuit. So it means our measurements are going to be made relative to the emitter. This is a 1K. We're going to call this RC. It's just a generic name, and this is a 1K. This is 12 volts. So what I wanted to do is I wanted to try to get the resistor. I wanted to try to get 6 volts right there. So what we're going to do is we're going to use a beta of around 100. So what size resistor would I use right there to get 6 volts right there? Tell me where to start. What 2 things? We got to know 2 things about something, right? So what 2 things do I know right off the bat? Okay, but about the circuit. That's a good point, but about the circuit. Well, we know how much. You're right, but I don't know the resistance of the transistor. The problem is the transistor resistance is a dynamic device. It varies, but I do know that 1K. I do know I have 12 volts on one side of it, and I do know I have 6 volts on the other. Right? You understand? So how much voltage is being dropped across RC? Okay, so I can calculate IC, and IC would be equal to 6 divided by 1K. So what would be the current through that resistor that I'm trying to get? 6 milliamps. Everybody okay? That's what I'm trying to get. So we'll set this up. We'll see. Go ahead. Oh, this is supposed to have an error on it, guys. I want 6 volts across the transistor. Well, if I want 6 volts across the transistor, then that means this guy here has to drop how many volts? According to Kirchhoff's law. So Kirchhoff's law says the sums of the voltage drops have to equal to the applied voltage. So I say if I got 6 volts across the transistor, what do I need to get to drop 12 volts? I need 6 more volts, right? You understand? Yes or no? You're kind of giving me that. Tell me what you're confused about. So if I came over here and gave you this series circuit right here, and I say I have no idea what that resistor is right there, but I know it's dropping 6 volts, and I know I got 12 volts right there. Yeah. Okay. So we got 12 volts. So I know this guy. I know the size of this resistor, right? You understand? Okay. So that means okay, I can calculate the current. So I'd say what? IC, this is the collector current, would be equal to 6 volts divided, 6 volts divided by 1K, which would give us 6 milliamps. Of course, now I know the transistor's got 1K worth of resistance. How do I know that? because they're dropping the same voltage. It's a series circuit, right? But this guy can change. This guy right here can't. This guy right here can change, right? You understand? Yes or no? Huh? Yeah, this is so what we're doing is we're operating this thing in the active region, so the transistor is acting with a rheostat. So what can I do with a rheostat? I can adjust the what? Current. Okay, so what if I say I want this guy here to drop 4 volts? That means this guy up here has to drop what? He's got to drop 8 volts. So now this is going to be 1K, right? You understand? This is going to be 8 milliamps. So what would the resistance of the transistor would be? Well, it's going to drop 4 volts at 8 milliamps. What you got to understand is the resistance of the transistor changes. It's a dynamic device, right? You understand? All I got to do is change base current. So what we're doing to control that resistor right there is we're controlling this with base current. But what I'm trying to do is get 6 minutes. So let's go back to our original one. We could do that, but I'm going to try to show you what happens when we heat this thing up. So if I increase the base current, this resistance goes down, which means the transistor drops less voltage, the resistor drops more. If I'll decrease my base current, then my transistor drops less voltage, and my transistor drops more voltage, which means my other resistors got to drop less because of Kirchhoff's law, right? You understand that? So if you can look at a transistor as 3 different methods, if you can look at the transistor as this, then you got it. But what's controlling that? So a rheostat, who controls the resistance of a real rheostat? You do. You have to turn a knob. What's controlling the resistance of this rheostat? Base current. But we can change it all over the place, right? So we got 3 options. We can operate it like this, or I can operate it like this. We call this saturation. So how much voltage will the transistor drop now if it's a closed switch? Yeah, even if this is 12 volts, so that means that guy right there is going to drop all the voltage, right? You understand? So this guy would drop 0 volts. And if I come over and do this and open up the switch, then how much, and that's 12 volts. How many volts would the switch, how much volts would the transistor drop? You're killing me. So how much resistance does an open switch have? Infinite. How much current flow is there in the circuit? None. So if V is equal to I times R, then V is equal to 1K times 0. So how much voltage would that resistor right there drop? 0. If it drops 0 volts, that means that 12 volts is sitting right there. Y'all understand that? So in a series circuit, the entire voltage appears across the open. So if I came over here and measured across these wall light switches right now, for all these lights, what would they measure across the switch? 100 what? 0. Because why? Yeah, well they have no resistance. Even though these guys might be pulling 1,000 amps, which they're not, that switch has no resistance, right? You understand? Unfortunately, a transistor cannot have no resistance. So let's talk about this. But if I go over there and open the switch and put my meter across it, it does what? It's going to show me 120 volts or whatever we have here, pretty close to that. Okay, guys, what size resistor do I need right here? I'm going to set this up to plus 5 volts to start off with. So I'm going to turn my pot all the way up. So what size resistor would I think I would need right there? We're going to use a beta of 100. So IC equals to what? Beta equals to what? Good. So beta equals to IC over IB. So I just calculated my IC. So what will my base current be? So what would IB be equal to? Yeah, so it would be equal to IC, which is 6 milliamps, and we're using a beta of 100. So I want to calculate a resistor that's going to drop 4.3 volts. So R is equal to V over I, 4.3, because we're putting 5 volts on that side. The transistor drops about 0.7. 4.3 divided by 60 micro. Transistor. Yeah, so this is the path right here. So this is this circuit right here. And Kirchhoff's voltage law says that the sums of the voltage drops have to equal to the applied voltage. I'm putting 5 volts right there. That's going to put a plus 5 on this. It's looking for a what? It's looking for a plus. The emitter is toward the negative, so that means this circuit is complete. The transistor drops between the emitter and base. It drops approximately what? 7/10. That means I've got to have 5 volts to this loop right here. Okay. So that's where the 4.3 came from. You okay, Bernard? Yeah, that's what we assume. All I know is it's somewhere between what? That's all I know. Typical beta for 3904, we played with these a lot, is around 100. I didn't say 800, I said a what? Around 100. So that's why I had to go to the pot, guys. But it gave you a good shot at it. So what size resistor would we use right there? Yeah, 71.6. So we didn't have a 71.6K. So I'm using I put a blue, I can't tell that color, guys. Blue, black, red. Oh, that's not even an orange. No wonder I was having problems. Oh, no, I changed it out. That is a blue, black, red. Good gracious, I'm going colorblind. So what was a 71 KB? No, yeah. No, 71. You're purple brown, right? Sorry. Everybody agree with that? Or violet. We usually call it violet, but that's okay. Everybody agree with Matt? And trouble is we don't have anything like that. Let's see what we got. I got a 3.3K. I got a 2.2K. This is a, here you go, Bernard. Pass this around. Let me see what size resistor y'all think this is. I don't have anything that size. And we can measure this, guys. But so what size do you think that one is, Bernard? You don't know what to do. Pass it back to Matt. I can't tell if that's red or orange. Go ahead. Yeah, I just yeah. So we got two power sources. We have VBB, which is setting the base voltage, and it's a pot. So what can I do with a potentiometer? Well, the potentiometer, I can adjust it all the way up here. I would get 5 volts. If I adjust it all the way down here, I'd get 0 volts, right? And so basically, right now, I could get any voltage between 0 and 5 volts out of that pot. And that's what's nice about a pot. So the top of the pot, we call it the top. The top to the bottom, you can get any voltage you need between those two ranges. Now, of course, the current, we're not worried about current right now, right? You understand? That makes sense? Any more questions? So beta is like Ohm's law, right? All you got to know is this first formula, beta is equal to what? IC over IB. And then once you've got a 3-term equation, you don't even have to know algebra anymore. You can just do what? You just cover up what you want to solve for. So what size is the resistor? Red, 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 red. Red, red, red. What do you think that is? And it's not a 5-band resistor. I'll show y'all some 5-band resistors too. So that's 2, right? 2, 0, no. And it's plus or minus 2%. Yeah, that's what the multiply. So the tolerance is a red. I mean, it's yeah, I guess you could call it a better resistor. It's just got a lot tighter tolerance, and it would cost more than a 5%, right? Now, 5-band resistors are usually at least 2%, and so 4-band resistors go number of zeros, right? Is that the way y'all learned it? Okay. A 5-band resistor goes number of zeros. And then, of course, after the number of zeros comes your what? Your tolerance, right? So this is the same here. This would be the tolerance down here too. These guys, some of them I don't even know. I think there's a purple or violet that's available, which is the tolerance for about 0.5%. So it's kind of weird. The red is easy. The brown would be easy. So brown would be 1% in the tolerance band. Red would be 2%, right? You understand that? But then after that, they get real weird. I'll try to get those to you. But these are what we call 5-band resistors. These are really low tolerance resistors, which means they cost more. So I'm using a 61. So that is an orange. I think it's a black. I'm using a 60K. So that means that my transistor is going to move towards saturation. So what I've got is I've got a 10K over here, so I can adjust it where I want it to. Everybody okay? So here's my camera. And here's my circuit. Oh, I need to get this out. I'm not using this. So here's my 6.1K. Here's my 1K. Here's my 2N3904. This is the emitter lead. It's connected to, I've got it connected to ground. Oh, by the way, here's my 5-volt supply. Y'all know that, right? Which we fixed yesterday. I mean, last class, right? So it's nice now. So what I can do, so notice I'm looking across the transistor. So this is the voltage across the transistor. And I'm going to turn my pot. And so now the transistor would be moving toward cutoff, right? So as it moves toward the power supply, it's moving toward cutoff. If the voltage drop across the transistor gets less, it's moving toward what? It's moving toward saturation. But I'm adjusting this. So here, we would be cut off, right? Because the power, sorry. So that's the power supply. So that's when I'm cut off, that means the transistor is going to drop all the voltage, right? And that means my resistor is going to drop none, right? Everybody understand that? So I can measure on this side of the transistor, it's 11.83 volts. On this side of the transistor, 11.83 volts. So that means across the resistor. So that means the resistor is dropping no voltage, right? And when do we assume it's saturated? We assume it's saturated when it drops less than a volt, right? And a transistor will never it's never a closed switch because it is not a switch.